So, today we will initiate the discussion regarding the ideal reactor. In previous session, we have discussed about the interpretation of batch reactor data with the tangible outcome that we have got a rate expression. And from all our previous understandings, we have got the rate expression for elementary, non-elementary, multiple reactions, single reaction, etc. Now, next we have to focus on these reactors. Now, you see, generally if I go through the different structures of reactors whatever are being used in process industry, we can see that majorly there are two different type of configuration. Tank reactor and tubular reactor. So, definitely as they are real reactors, so these two are in general non-ideal reactor. So, you see, in a tank reactor what we have? A tank, cylindrical tank fitted with a stirrer, we have inflow and we have outflow, right. Whereas in tubular reactor, we have tubes mostly loaded with catalyst, may not be loaded with catalyst as well. This is inflow, this is outflow. Here the diameter is in the order of height or length, right. So, let us call this is L and this is diameter. Whereas here, if this is the diameter and this is the length, D is much smaller than L. So, that is the physical characteristics we know about the tank reactor and the tubular reactor. Now, the point is, definitely we can understand that it is a concentration of the reactant, say the reaction is A giving product. Concentration is a function of R, theta, Z and T, and we fix our coordinate system from somewhere here, right. And here also the concentration, if we fix the coordinate here, the concentration of A is a function of R, theta, Z and T. So, the respective governing equation, we can actually derive this by writing the convection, diffusion, reaction equation, what we have studied in mass transfer. Now, you see that these many numbers of coordinates as well as time, right, it will make the system equation extremely complicated to deal with, particularly from this analytical perspective. Now, in steady state, it will be a function of R, theta, Z. This is also in steady state a function of R, theta, Z. So, steady state consideration is definitely necessary for design. So, we are thinking mostly of this reactor design, right. Our focus is reactor design for a given performance. Right. Now, even under this steady state condition, we have 3 coordinates. And the boundary condition, specifically the boundary condition is much easier to develop for tubular reactor, right? But it's quite difficult and extremely complicated for tank reactor because we have a rotating stirrer. So, we further try to simplify. First, what do we do? Axisymmetry. That is del Ca del theta is 0, right. Now, you see actually here it is not, because if you see from the top we are giving the inflow at some specific location, but still if you think that okay, we are delivering the reactant somewhere over here at the central location, we can tentatively think of axisymmetry, and from this axisymmetry we have the steady state equation as Ca as a function of r and z only, right. Still we have 2 coordinates. Now, what do you think that in this case, if we think of tank reactor, or we think of an idealization scheme of tank reactor, we will assume this is perfectly, the reactant and the product are perfectly mixed, or in a perfectly mixed state. So, if it is perfectly mixed, that is del Ca del r and del Ca del z becomes 0. There is no variation of concentration with space coordinate. Now, obviously one may ask that here where we have the inflow, this concentration, let us say Ca naught, and the outlet concentration is CAF or Ca, right. So, everywhere if I think it is same, then definitely it must be is equal to Ca even at this point, at the inlet point, right. So, we introduce a model of the idealized model of a tank reactor, that instant conversion at the inlet port of the reactor the converted reactant and converted and unconverted reactant are transported to the outlet, right. So, in a sense it behaves like a step function. That is, say if I am, this is Ca, this is time, right. If I am giving this at Ca naught, it is simply converted to Ca in a single step here, right. So, this gives you the idea of mixed flow reactor or continuous stirred tank reactor. That is, we may call it MFR or CSTR. Right? So, that is an idealization scheme of the tank reactor. Whereas here, in case of this tubular reactor, we cannot think that this entire content is perfectly mixed because it is traversing in a specific direction and there is no stirrer. Right. So, here we consider perfect radial mixing. Right. That is del Ca del R equal to 0 and no axial mixing. Right? No axial mixing. So, this no axial mixing, it is only possible if there is no dispersion of the concentration front So, in diagram we may represent that concentration at any point will be something like this. It is not like this, right? This we assume. Okay. So, this condition of zero dispersion is only possible if we have a very high bulk velocity, or rather the average velocity very high average velocity such that the velocity profile becomes flat like infinite Reynolds number flow. So, when Reynolds number tends to infinity, the profile becomes flat, it is extremely turbulent, right? And this we call plug flow, slug flow, piston flow, etc. Here we have Ca as a function of Z only, right? And the corresponding reactor is called the plug flow reactor or PFI. So, you have to understand that CSTR is finally an idealization of tank reactor, whereas PFR is an idealization of tubular reactor. So, that is the entire idea of the ideal reactors. One is PFR, another is CSTR. PFR is an idealization of tubular reactor, where CSTR is an idealization of tank reactor. And the scheme of idealization we have discussed. So, with this understanding, let us move into the design equation of these two ideal continuous reactors or the flow reactors, right. So, but before that we need to define a very important common terminology which is applicable to both of them, and that's called the space-time. Right, that's called the space-time. So, space-time generally represented by tau for a continuous reactor. So, this is the time required to process one reactor volume of the reactant under specified physical condition. Right. Just like for a tubular reactor, if this is a tubular reactor, so we think of the reactant volume entering this and also leaving from here. Right. So, this reactant volume, it enters the reactor and leaves. So, what is the time of its traverse to the reactor? That is basically the space time. Okay. So, let the volume of the reactor be V and the volume flow rate of the reactant be V naught. Then tau is definitely V by V naught. Right, this is a volume basis, and you can understand that why I have given specific physical condition, because this V naught depends on temperature and pressure, right, in general. Now you see that here we have used these volume based notations. We can also write it in terms of this amount of material, that is mole basis notation, right. So, the material or the reactant or the number of moles of the reactant in the reactor is Ca naught into V, right. Molar flow rate is Fa naught. So, tau is also equal to V into Ca naught by Fa naught. So, we have a very important unique relation for continuous flow reactor, that is tau by Ca naught equal to V by Fa naught. Right. So, with this understanding of space time, sometimes we refer this space velocity as the number of the reactant volume, the number of the reactor volume of this reactant which is being processed per unit time, right. This is inverse of simply tau, but that we do not use much in this entire discussion, standard elementary discussion of reaction engineering. So, we focus on the space time. Now, with that understanding of the space time, Let's now go for solving the design equation, right? That is a steady state material balance equation for Cstr and for Pfr independently. So, design or steady state performance equation of Cstr. Now, you see here it is Ca naught, V naught, Fa naught, Xa naught. Right, generally for the first time we consider it to be 0, and it is unreactant or unreacted reactant. Here it is CAF, XAF, FAF, and the volume is V. So, we will write the equation as input is equal to output plus accumulation plus disappearance by chemical reaction. So, this will be a component balance equation. So, here what will be the input? It will be simply Fa naught. What will be the output? FAF. Accumulation is 0 because it is steady state, and disappearance by chemical reaction minus Ra into V. Right. So, that is the issue basically. Now, FAF we can write as Fa naught into 1 minus XAF, molar flow rate. So, which is minus Ra into V, and this is Fa naught only. So, we have this Fa naught into XAF, and this minus Ra at what? At final concentration, because in this everywhere the concentration is CAF, even here. So, Fa naught into XAF is equal to minus Ra at F into V. So, we have the final design equation as V by Fa naught, which is also just we have proved, it is equal to tau by Ca naught is equal to XAF by minus Ra at F. Right. So, that is the design equation of Cstr. Now, for constant volume system, V naught equal to Vf. Here volume flow rate is Vf, here the volume flow rate is V naught. So, under this situation, tau is equal to Ca naught into XAF divided by minus Ra at F, and that is equal to Ca naught minus CAF divided by minus Ra at F. So, that is the equation for constant volume system. We have a graphical interpretation as well for this design equation. Let us say this is equation 1. So, here we have Xa, here we plot 1 by minus Ra, and generally for positive ordered reaction it will be like this. Why? Because you see that Ra decreases with concentration, because Ra has got a monotonic relation with concentration, right, just like for first order reaction minus Ra is proportional to this Ca. And so, from the beginning the Ca decreases from Ca naught to Caf, right, and this Xa increases So minus Ra must decrease with Xa, and essentially 1 by minus Ra must increase with Xa if the reaction is of positive order. Right. So if I have leveled that this is XAF, so it is, and this will be minus 1 by minus Ra at F. So this area under the curve, or this rectangular area, is basically V by Fa naught, which is tau by Ca naught for Cstr. Right. So even if we have a negative ordered reaction, if we have a negative ordered reaction where 1 by minus Ra versus Xa is just like this, and this is my XAF, so you can see that this will be the area. This is 1 by minus Ra at F, so this much is tau by Ca naught equal to V by Fa naught for Cstr. So that's the basic design equation for Cstr. Now next we'll try to solve for this design equation of Pfi. So for Pfr, you have to note that minus Ra changes with Z, the length of the reactor. So this design equation for Pfr, it's like this. If A naught, Ca naught, V naught, Xa naught equal to 0. And here we have FAF, CAF, VF, XAF. Now you see that concentration is a function of Z, Xa is also a function of Z. So just if I draw a qualitative plot, this is Z 0 to L, and here if I plot Xa, we can see that this will be increasing. So Xa or dXA dZ is positive, right? It looks like a straight line, actually it is not, it will be curved, right? So it will be increasing unless it saturates to 1. So you see, it's in general a distributed parameter model, contrary to the previous one, the Cstr, which was this lumped parameter model, as there was no variation with respect to space coordinate. This is a distributed parameter model of reactor. Definitely simplified, because in actual reactor this perfect radial mixing cannot be assumed. So the dimensionality of this problem increases from only CAZ to CARZ. So anyway, so whenever it is a distributed parameter model, we have to go by this differential control volume analysis, contrary to the previous Cstr, where we have used the integral, that is, means the control volume is over the entire, incorporating the entire reactor. So the differential volume is like this. This is the differential control volume or the shell, right. Differential control volume is often represented or stated as shell in the terminology of transport phenomena. So anyway, here we have Fa at Z. Here we have Fa at Z plus delta Z. Let's say the thickness is delta Z. So write the same equation even for the differential control volume, that is input is equal to output plus accumulation plus disappearance by chemical reaction. Right. So input to this differential shell is Fa at Z, output be Fa at Z plus delta Z, accumulation is 0 because it is a steady state case, plus minus Ra into say A into dz, where A is the cross sectional area. Of the reactor. Right. So you see this, if I switch this term on this side, we can write that minus of this Fa at Z plus delta Z minus of Fa at Z divided by delta Z is equal to minus Ra into A. Right. So this is minus of dFA dz. So this is minus Ra. Now Fa, again, Fa is Fa naught into 1 minus Xa. So dFA is minus of dxa into Fa naught. So if we substitute it back, so it will be Fa naught into dxa dz, which is minus Ra into area here. Now we may group this Z with area as Z into A, because area is constant, equal to minus Ra, and that gives you Fa naught into dxa dV as minus Ra. So it's obvious that if we integrate, we will get V by Fa naught integral 0 to xaf dxa by minus Ra. So that becomes the design equation or performance, steady state performance equation of Pfi. Steady state performance equation of Pfi. And essentially it is equal to tau by Ca naught, because V by Fa naught equal to tau by Ca naught. So next you see that we have V by Fa naught equal to tau by Ca naught 0 to xaf dxa by minus Ra. Now for constant volume system, tau is equal to, as it is constant, dxa into Ca naught divided by minus Ra. So it becomes 0. So it will be Ca, we know that for constant volume Ca naught into 1 minus Xa. So dCa is equal to minus of Ca naught into dxa. So dxa into Ca naught with a minus sign, so there will be minus dCa by minus Ra from Ca naught to Caf. Right. So that can be simplified for constant volume systems. So anyway, and the graphical interpretation. Now for positive ordered reaction, 1 by minus Ra versus Xa, it will be like this. This is Xaf, so it is the area under the curve. So this is V by Fa naught equal to tau by Ca naught for Pfi. Right, for positive ordered. For negative ordered, it will be like this. This is Xaf. So this is V by Fa naught equal to tau by Ca naught for Pfi. So that's the design equation for Cstr and Pfrs. Now you see, if I now think of some specific cases, like we may think of first order equation, right, for constant volume and variable volume. Let's see what we will get. Now let's say it is a first order constant volume reaction. Minus Ra is equal to Kca is equal to minus of dCa dt. So Cstr, tau by Ca naught equal to this Xaf by minus Ra at F, which is Xaf by K into Caf. So what you can write that tau is equal to Ca naught into Xaf by K into Caf, and that is Ca naught minus Caf divided by K into Caf. So we have 1 plus K tau Caf is equal to Ca naught, and finally the Caf equal to Ca naught divided by 1 plus K tau. Right. So that's the final equation. Now for variable volume, first order, minus Ra is equal to minus of 1 by V dna dt. Right. So that is Ca naught divided by 1 plus epsilon A Xa into dxa dt, that we know, and minus Ra alternatively, that's equal to Ca naught into 1 minus Xa divided by 1 plus epsilon A Xa. So we have tau by Ca naught is equal to Xaf divided by minus Ra, which is K into Ca naught into 1 minus Xaf into 1 plus epsilon A Xaf. Ca naught cancels out, so K tau is equal to Xaf 1 plus epsilon A XA F divided by 1 minus XAF. So that's the final form of the design equation for variable volume. Right. Now for second order constant volume, unimolecular reaction, 2A giving product. So it is tau by Ca naught is equal to XAF by K into CAF square. So tau is equal to Ca naught minus CAF divided by K into CAF square. So K tau into CAF square plus CAF minus Ca naught equal to 0. So CAF is equal to minus 1 plus minus root over of 1 plus 4 K tau divided by 2A. So that is 2 K tau. So minus sign will be cancelled in order to have this positive concentration. Right. So that's the idea. Now if I think of second order variable volume, unimolecular reaction. So what we will have minus RA is equal to KCA square. So that is K into Ca naught square 1 minus XA square divided by 1 plus epsilon A XA whole square. So we have tau by Ca naught equal to XAF divided by K into Ca naught square 1 minus XAF whole square 1 plus epsilon A XAF whole square. So if I have to solve, so that is K tau is equal to XAF 1 plus epsilon A XAF whole square divided by Ca naught into 1 minus XAF whole square. So if I need to solve this XAF, we have to go for solving this cubic equation, and we can go for trial, and from there we can solve for this XAF. Right. Now for PFR, what will happen? This was Cstr, the standard elementary reaction we have discussed. They integrate the standard form. Right. Now the PFR calculation is a bit complex because of integration relative to that of Cstr. So for PFR, first order reaction, constant volume minus Ra is equal to Kca. So tau by Ca naught is equal to dxa divided by K into Ca naught into 1 minus Xa integral from 0 to Xa f. So Ca naught cancels out. So K into tau is equal to minus of ln 1 minus XAF. So this you see structurally very similar to batch reactor, because in a batch reactor what we know, we have this minus Ra is equal to Kca, which is K into Ca naught into 1 minus Xa, and this minus Ra we can write it as Ca naught into dxa dt is equal to K Ca naught into 1 minus Xa. So we have the Ca naught cancels out. So minus of ln 1 minus XAF is equal to K into T batch, the batch time. Right. And structurally, you see, the constant volume Pfr. The equation is tau by Ca naught 0 to Xa dxa by minus Ra. For batch, the thing is minus of or plus of Ca naught dxa dt is equal to minus Ra, right. So, you see that Tb by Ca naught after integration 0 to Xaf dxa by minus Ra. So, they are identical to each other with tau and Tb interchanging. Right. So, you have to simply, we are going for this plug flow reactor, we have to interchange or replace this tau by Tb, and we have to get the final form of the design equation. So, design equation for a constant volume systems are same as batch reactors, right. So, from here we can conclude that integrated form of design equation for constant volume systems are same as batch reactor. So, you see for first order variable volume, what we have? V by Fa naught equal to tau by Ca naught 0 to Xa dxa by minus Ra. Minus Ra equal to K into Ca naught into 1 minus Xa divided by 1 plus epsilon Axa. So, the Ca naught cancels out. So, we have K tau integral 0 to Xaf, here Xaf, or numerator we will have 1 plus epsilon Axa, denominator 1 minus Xa dxa. So, after the first integration we will have minus of ln 1 minus Xaf plus epsilon Axa, here what is the integral? 0 to Xaf epsilon Axa by 1 minus Xa dxa. So, what you can do? Epsilon A we can take here, right. So, we will write minus 1 and 1 plus. So, this K tau becomes minus of ln 1 minus Xaf, minus of ln 1 minus Xaf minus of epsilon A. If we take this minus common from this part, minus of epsilon A into Xa, and 1 divided by 1 minus Xa. So, that is minus of epsilon A ln of 1 minus Xa. So, it is minus of 1 plus epsilon A ln 1 minus Xaf minus epsilon A Xaf, and that is K tau. So, that is the integrated form for first order variable volume reaction. So, similarly we have to go for complex bit difficult integrations for this variable volume, like 2A giving product. I am not doing this integration, 2A giving product. So, it is Ca naught into K into tau equal to 2 epsilon A 1 plus epsilon A, right, ln of 1 minus Xa plus epsilon A square Xa plus 1 plus epsilon a square xa by 1 minus x. So, here if you put this epsilon a equal to 0, you will get back the performance of a constant volume Cstr. So, yeah. Now, another very important issue regarding solving problems, let us discuss. Reactor with two streams. Like I have a Cstr, here I have V1, a stream volume flow rate, its concentration is Ca1 and Cv1, another V2, concentration Ca2, Cv2. Now, what will be the Ca0 and Cv0? So, it is obvious that we will write this V1 into Ca1 plus V2 into Ca2 equal to V1 plus V2 into Ca0. So, Ca0 becomes V1 Ca1 plus V2 Ca2 divided by V1 plus V2. Similarly, Cv0 equal to V1 Cv1 V2 Cv2 divided by V1 plus V2. Right. So, that technique we have to use to solve for this Ca0 and Cv0, and with that we will further go for solving problems. Like okay, just this is a batch problem. Let's solve this. Okay, but let's do this later, maybe in the next session, right? But before that, let's proceed to the comparison of reactor area or reactor volume necessary to perform this Cstrs or this reactions in Cstrs and Pfrs. So, you see we are going to have a comparison between Cstr and Pfr, right. So, first positive ordered reaction n greater than 0, right. So, we have here the curve of 1 by minus Ra versus Xa be like this, and let us say this is Xaf, correct. So, what we have discussed so far, this dotted area will be the V by Fa0 or tau by Ca0 for Cstr, right. So, V by Fa0 for Cstr equal to this dotted area, and for Pfr this will be the V by Fa0. So V by Fa0 Pfr this area. So you can easily understand that V of Pfr is lower, much lower than V of Cstr. So V Pfr is lower than V Cstr, and the reactor which needs lower volume, that means lower capital cost, capital investment, is definitely advantageous. So Pfr is recommended for reactions with n greater than 0. Right. Second, negative ordered reaction, n less than 0. So here we have 1 by minus Ra versus Xa, a monotonically decreasing profile like this. Now here let's say it is XAF. So this will be the area for Pfr and this, sorry, for MFR, and this will be for Pfr. So V MFR or CSTR, whatever, it's this hatch and dotted area. V Pfr is equal to this dotted area plus this hatch and dotted area. So V Pfr is greater than V CSTR. So we recommend CSTR. Right. Now things are not so universal and clear for systems where we have a non-monotonic profile of 1 by minus Ra versus Xa. So third, and that happens for autocatalytic reactions. Now you see A plus R giving R plus R. So minus Ra is equal to K into Ca into Cr. So that is K into Ca naught into 1 minus Xa into Cr naught plus Ca naught into Xa. So obviously K into Ca naught square 1 minus Xa into M plus Xa. Right. So 1 divided by minus Ra is equal to 1 divided by K into Ca naught square 1 minus Xa divided by M plus Xa. Right. So if we are trying to locate the possible existence of maxima and minima, so that is K into Ca naught minus sine 1 minus Xa into M plus Xa whole square, then there will be a minus sign here. So it is M into 1 minus Xa plus M plus Xa into minus 1, and that we will set equal to 0. Right. So if you drop this minus, so M minus Mxa plus M, yeah. Yeah, what is happening? M minus Xa plus M, minus M minus Xa. Yeah, it should not be. Just a minute. Mxa. So it is M into 1 minus Xa, fine. M minus Mxa Okay. Here we have done the mistake. Here it will be 1. So it is 1, right. So this is 0. And this will be also XA. So XA star is 1 minus m divided by 2. So at which the 1 by minus RA will be passing through a minima. So if you take the second derivative, so d square dxa square 1 by minus RA at XA star is positive. So it is a minima. And the graph of the plot of 1 by minus RA versus XA will look like this. And here we have this XA star. Now, if this is the reaction kinetics, then what will happen for Cstr and Pfr? So we can think of a situation, see, where a concentration XAF prime for XA equal to XAF prime, V of Pfr, let's assume, equal to V of Cstr. So what is the graphical interpretation? So 1 by minus RA, this. Now let's say it is somewhere over here, XAF, right, prime. So this is the area for Cstr. So this V Cstr equal to this hatched area, right. Whereas Vpfr will be this area under the curve. So we can write that Vpfr is equal to this plus this one, there will be a hatch and dot, another is dot only. So this area, unhatched area, and this only hatched area, if they are same, and it must be same to have this VCSTR equal to Vpfr. So for XA is equal to XAF prime, this VCSTR equal to Vpfr. Now for XA less than or XAF less than XAF prime on this side, right, what will happen? Here definitely VCSTR will be less than Vpfr. We recommend CSTR. And additionally for XAF greater than XAF prime, Vpfr is less than VCSTR. So Pfr is recommended. Right. So only for autocatalytic reaction, the reactor, the optimum reactor, that depends on the desired value of final concentration. But for positive ordered or negative ordered non-autocatalytic reaction, for positive ordered we recommend Pfr, for negative order we universally recommend CSTR. There is no question of what, or no question will be asked that what will be the final desired conversion. But here for autocatalysis you can see that If there is a threshold concentration, if my final concentration or final conversion is less than this threshold, we recommend this MFR, and if it is higher than that threshold, we recommend this Cstr. And at that threshold, PFR and Cstr's volume are same, so anything will be fine, right? So that's all about the basic comparison and the design equation of MFR and PFR. So in the next session, we will start discussing about the PFR and CSTRs in series or parallel combination.